Hello and welcome. Today is April 21st, Tuesday. We are nearing the end of April. Actually, there's still one more week. Uh, Today we'll go over a bit more on complex circuits, learn about the current divider rule. This should help us analyze circuits at a much more efficient rate in that we're able to now directly find how much current goes through each branch in a circuit without knowing what the voltage is, right? Uh, you should have looked at least what the mastering at the second mastering physics homework, which is due next Monday. It should have been opened right after the stream yesterday. Mr. Hussey has released a new email regarding a schedule change in our school system for the time being for the rest of the semester. In that Wednesdays, teachers will be having meetings and stuff, like virtual meetings and phone meetings. So Wednesdays, there will be no streams. So our streams will be only Monday, Tuesday, Thursday, Friday. No streams on Wednesdays. No streams on Wednesdays. So class is only 4 days a week now. 4 day per week classes. So it's Monday, Tuesday, Thursday, and Friday. Yeah, every Wednesday, no stream. Yeah, it just means we're gonna get stuck in like meetings and stuff. We have to develop some new rules and how we're going to do finals and all this other stuff that's got to happen in the next month or so. So that's why we're gonna have meetings every day. Oh boy. So yeah, today's a downer for sure. Seems like. Uh, but we'll make the best of it. Does this mean we will not be getting work assigned on? Well, I'll just assign you work. That's I never assign you daily work, right? I assign you like weekly work. So, I mean, I give you work that you have like a week to do, and so for us, nothing will change. It's just you won't be here, watching streams on Wednesdays. That's the only difference. So you'll be doing your mastering physics homework or whatever it is on Wednesday, or studying or whatever it is. I don't know what the other teachers will do. I'm guessing that they'll assign something Tuesday, and then it'll just carry over, most likely. But ideally, there's nothing new that's going to be given on a Wednesday. But obviously there are loopholes around that. Just give a bunch of stuff on Monday, or just do projects. Here's a project. It's gonna take you a week to do. Here's a research paper. It's gonna take you 2 weeks to do. Here, read a book and do a book summary or something. I don't know what they're doing. Whatever English teachers do. So anyway, so that's that. So again, reminder: no streams on Wednesdays. So that if you take a look at our calendar, we're supposed to do a lab or something. We'll do our complex circuit lab thing activity on Thursday then, so it'll get pushed back one day. Yeah, things are changing like every day. We get like hundreds of emails. It's crazy. It is crazy. And what's crazier is some people in other states are protesting the shutdown, the stay-at-home orders. Yeah, but luckily it's not happening in California. Oh, stocks are down. That's not good. All right. So let's take a look at the current divider rule. Current divider rule. Current divider. Alright, so let's have a nice circuit with a resistor, another resistor. Here's another one. Whoa, it's sideways. Here's R1. Here's R2. R3. Whoa. Take a look at that. How are R2 and 3 related? Oh, really? Huntington Beach? That is. Uh oh, it's spreading, huh? That's not good. Well, if we follow the current flow diagram, as you can see, we always start from the positive side, which is the big line. Comes out, of course, all of it goes through a resistor 1, and then we hit this fork in the road, and now we have two pathways to go through. But after going through these pathways, you'll see that they both meet up again. Okay. Now, the current that went through resistor 3, let's use green. This green one, well, can it go up the stream, up the waterfall against gravity? Or in this case, against the electric current, or not quite. So it can't go upstream. Once you're down at 0, you have to go up the battery to get up again. So once you're down here in the bottom floor, you're kind of stuck. It's like, doing making a roller coaster or something that has two different endings. But at the end of the day, once you're at the bottom, you got to line up, get in line again, so you can climb the stairs all over again, right? All right. So even though I drew it weird, R2 is parallel to R3. Okay. Parallel means that the current splits and recombines after passing through the resistors. Not that they are oriented geometrically in parallel. So geometry doesn't have anything to do with it. It's just the current. If the current splits and combines again, then it is parallel. So let's get some values here. So far we know that the total resistance, rec, in the system should be R1 plus the parallel of R2 and 3. Right. The other thing that we know is that the total current goes through resistor 1, so we can say that I total is equal to I1. Now it does not equal I2 and 3. That's because at this blue junction here, it splits up into two pieces. I should use a different color. Here, let's use a different color. Oops, that's not different. I'll use pink. So it splits up into pink and green. And then it will recombine again at the bottom to turn to blue again. There we go. Now I2 and I3 will split up based on the resistance values in each branch, in each lane, in each pathway, right? So the current splitter rule, so here's the current splitter rule. It's great for 2 lanes only. The current in the first pathway, so in this case our first pathway being R2, so the current in first pathway is equal to a proportion, a percentage of the total. Whatever's coming into our junction, well, in this circuit, I total is coming into our junction. If we look at the junction only, so this blue dot here, slightly darker, there we go. So at this blue dot we have I total coming in, or I1, doesn't matter, because they're both equal. And we have I2 and I3 leaving this junction. Okay. Oh, my arrow does not look very nice. So I3 and I2 are leaving the blue dot, while I total or I1 are both going, it is going into the blue dot. So I2 will be a percentage. Now what percent? Well, it's basically a inverse relationship in that it's not based on the amount of resistance it has. So I2 is dependent on the resistance of the other branch. So meaning if you have low resistance, then you'll get more current. And if you have more resistance, you'll get less current. So I2, the pink one, these colors, so the pink one is equal to the opposite resistor being R3, divided by the sum of the two paths, R2 plus R3. Okay, so let us dissect this a little bit. So the numerator is the opposite resistor, or other, the other branch. And the bottom, I'm running out of colors. Let's use orange. The bottom is the sum of the two paths. Okay, so it's important to note that it's the paths, not necessarily the individual resistors, such that in the future, if we have multiple resistors in a path, then you have to combine those resistors first, and then you can do this. Okay, so following this pattern, this means that the current in resistor 3, so the green path, which is I3, must be equal to the opposite resistor to path 3, so the opposite being the other branch, which is R2, divided by the sum of the two paths. The denominator does not change. R2 plus R3 times the amount that goes into the junction, which is the total current in this circuit. Okay, so this is the current splitter rule. Using this, we're able to kind of get the current directly without knowing the voltage. Of course, the other way to find the current is to find the voltages first and then dividing voltage by the resistances to get the individual current. Right? Recall that I2 must also equal to, using Ohm's law, we can see that it must equal the voltage in resistor 2 divided by the resistance in resistor 2. So similarly, I3 must also equal the voltage in resistor 3 divided by resistor 3. Okay, so Ohm's law still applies. This is just another way to find the current. Uh-oh, what is this line? Let's clean it up a little. There we go. All right. More of our students are sleeping in these days. Every day we're staying up later and later, I guess. And they're sleeping in more and more. All right. So let's see if we can apply this to a more complex circuit. We'll do 4 resistors, and we'll do an entire set. So here's an example. Here's voltage. All right, someone chat. Someone give us some numbers here. How many volts should our battery be? Okay, no. No preferences, huh? Oh, we got one. All right, 12 volts it is. A 12-volt battery. All right. I need some easy numbers for our resistors. Some easy numbers for resistors. Let's call this R1, R2, R3, R4. All right. Let's make a quick chart here. Can I do a chart? Yeah, I can. How many? Well, I need 4 resistors, 4 currents, 4 voltages, 4 powers. There we go. Ah. No, how do I? Okay. I think I need to use my mouse. We got some numbers. We got 5 and okay, so let's use some. Let's make a table here. I need my table to be bigger. This is not working out. Oh, that didn't work. Ah. Okay, it's not bad. Right, I need values for resistor 1, resistor 2, resistor 3, and resistor 4. We got 5, 6 to drag from the bottom right. Yeah, I was trying to do that, but the little, see how it's like horizontal? It's just not working out. The little sideways diagonal thing is not popping up, so I have to do it manually. Yikes. Great, I can't make it bigger. Oh well. I'll just type it in, I guess. This is R1. In R1, let's see, we have 5. I see a 5, so let's do 5 ohms. Oh, it looks like 50. Let's put a space. There we go, 5 ohms. R2 is equal to, we got a 6. Chapito says 6. All right, 6 ohms. I see a 2. I need one more. So, oops. So R, oh, I can hit a space. Yay, that makes it nice. R3, that'll be 2 ohms. 2 ohms. And then R4, which is drag from the bottom. Yeah, I already read that. I need one more. Let's make it easy. I don't know. 1. I want to use easy numbers. Ohms. 1. All right. That's good enough. That's good enough. Thank you for the suggestions. So our chart will be, resistors here. This will be the current chart. Current. And this will be our voltage chart. Voltage. And this last one will be the, I'm saying chart, but what I mean is columns. This column will be the power, capital P. All right, so let's see. I'm just gonna see if I can write. Oh, I need one more space here at the bottom one. The bottom one. Now I have enough space to write. Okay, so current flow diagram first, just so that we know what is happening in our circuit. So out of the plus end and goes through our first resistor, and then we hit a junction here, a fork in the road, and then some of it will go through resistor 2, some of it will go through this path instead, and then eventually they'll meet up again, and now we're at the bottom of the battery. Okay. Things that we can do, of course, we can find rec. Oh, I forgot the fifth row. Whoops. Oh well. We'll put rec over here. Rec. Always start with rec. It's, if you have your resistors, just see if you can combine them. All right. So we look for patterns first. If the same current goes through any two resistors, those two resistors are in parallel. Oh, so, oops, I said that wrong. Ignore what I just said. If the same current goes through two resistors, then the two resistors are in series, not parallel, series. But if the current splits and recombines, then they are parallel. Now in this setup, you'll see that whatever current goes through resistor 3, okay, has to go through resistor 4 before it can meet up again. Therefore, these two resistors are in series because they're one after the other, right? Now, R2 and 3 are not parallel. R2 and 4 are not parallel. That's because, 3 and 4 are first in series. The two branches are parallel, but the individual resistors are not parallel. We have to first combine 3 and 4 together to get this set up. R1, R2, and I'll replace that with the green resistor. And this green resistor represents the combination of 3 and 4. This is R34, which is equal to 1 over R3 plus 1 over R4. Okay, so after that, after combining 3 and 4, then you can say that these two are in parallel, because after the current splits up, some of it goes through R2, some of it goes through the combination of 3 and 4. Okay, so these two are parallel now. Let's use a different color, purple. These two are parallel. So we are reducing our circuit one step at a time. One strategy is to look away from the battery. Try to put or combine resistors together as far away from the battery as possible first, as it makes it easier for most of the time, of course. Okay. So if I were to write, oh, chat. So what do you see that is what do you see that is wrong here? Someone tell me what is something that I did that is incorrect. I'll give you a hint. I'm highlighting right here. What is wrong? What did I do wrong? R2? No, R2 is not wrong. Something about R34. What is wrong about R34? I don't know. Are you guys paying attention, or what did I do incorrect over here? You made them parallel instead of series. Excellent. 3 and 4 are not parallel. They're in series. So how do you find resistances of resistors when they are in series? You add them. Yes, there you go. So R34 should have been just R3 plus R4. Good job. And then once I do that, once I combine it that way, so let's see, R3 was 2 ohms, R4 was 1 ohm, so that's 3 ohms. Let's use omega. Omega. 3 ohms. And once I find R3, then I can use the parallel rule to state that R2, 3, 4, the combination of 2, 3, and 4 is equal to 1 over, now that I know these two are parallel, it is equal to 1 over R2 plus 1 over R3, 4. Okay, and after that, then we can add the last one. So we have our battery, we have our resistor, and now we've combined R2 and R3, 4. This gives us a new resistor, a purple one. And this purple one has a value of R2, 3, 4. And now we can see that number 1 is in series with the rest. Okay. So if I were to write it as an equation, rec was equal to R1 plus the parallel of R2, which is parallel to the sum of 3 and 4. Okay, so you have to add 3 and 4 together first, then take the parallel of R2 and 3, 4. Then you just add up the last bit. So let's see. If we do that, we get, so we got 3 ohms for R3. So this is 1 over, R2 is 6. So 1 over 6 plus, ooh, that doesn't look like a plus. 1 over 6 plus 1 over 3. 1 over 3. Or just use the product over sum shortcut, right? 3 times 6 is 18. 18 divided by 9 is 2. 2 ohms. And so if R2, 3, 4 is 2 ohms, and R1 was, how much was R1? 5 ohms. Then we have 7 ohms as our total. 7 ohms. Okay. This will help us find I total. I total. Okay. And we can just use Ohm's law. I total is equal to V total over the resistance total, which we call rec, equivalent resistance. And this will be 12 volts divided by 7. Oh, it was so close. I wish it was 14 volts. Oh well. 7 ohms. Alright. So, I don't know. What's 12 over 7? I never divide by 7. Ah, it's 1.714. Oh, I actually like, yeah, that's not bad. How many sig? Oh, we should worry about some sig figs. I don't like 1 sig figs. Let's make everything 2 sig figs. So just add a decimal point to everything. So this is 5.0, this is 6.0, this is 2.0, this is 1.0. This would be 7.0. So let's make everything 2 sig figs at least. This gives us roughly 1.7 amps. Voltage total is, of course, from the battery, and that's 12 volts. Power total would be the product of I total and V total. right? Or I can use v squared over r. Now you might be off just because we're rounding a little bit. So since 7 was really nice and I total was a rounded number, I'm going to use v squared over r. So this gives me 144 over 7, which is roughly 20.6. So about 21 watts. Should have used 3 sig figs, honestly. 3 is so much better. But oh well. If I used IV, I should get something similar, right? I times V. So that would be 1.7 times 12, which gives me 20.4. See, so you're off by just a smidgen because of rounding errors. I took the higher number just because the I total was rounded down. Of course, it's more like 1.714 dot 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 dot. Okay. Based on the current flow diagram, we can see how the total current goes through resistor 1, so we can say I total must equal I1. So 1.7 must be I1. 1.7 amps. Okay. But after we hit the orange junction, the fork in the road, we split up into 2 parts, right? Some of it goes through resistor 2 and the rest goes through resistor 3. We could use the newly derived current splitter rule to figure out how much current goes through resistor 2 and 3, or the other method is to find the voltages and then divide using Ohm's law. So let's try using the current splitter rule because it's fresh and new. Okay, the current splitter rule tells me that the current in resistor 2, I2, must be equal to a proportion of whatever's coming in, the total. The total is I total, again. The numerator is what is in the opposite branch. So opposite to R2, we have the combination of 3 and 4. So I'll put R3, 4 here. And in the bottom, we have the sum of the 2 paths. Sum of the 2 paths would be R2 plus R3, 4. Okay, so this means that we get R3, 4 was 3 ohms. 3 ohms. I'll just put 3 ohms. R2 was 6 ohms. R3, 4 was 3 ohms. Times the total, which is 1.7. Right? So 3 over 9 is a third. And look for patterns. What do you notice? Well, okay, you have double the resistance. You have half the current. Right, so 1 over 3 times 1.714 blah 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 blah. This gives me 0.57. 0.57 amps. So we'll put 0.57 amps for R2. Now you could use the current splitter rule for the other one too, if you wanted. The current through resistor 3, 4 must be equal to the opposite branch. So opposite to 3, 4 is R2 divided by the sum of the 2 branches times the total. And it's the total because the total is going into the junction. If something else was going into the junction, that's what you would use here instead of the total. So this tells you that it is 2 over 6 plus 3 times 1.7. 1, 4, blah, blah, blah. Okay, now we have 1/3 of it. 2 over 9. Oh no. Whoops. It's not 2. It's 6. R2 is 6. Wasn't R2 6? Yeah, R2 was 6 ohms, not 2 ohms. Yeah, I have it in the denominator. Whoops. So 6 divided by 6 plus 3. So that's 2/3. So it's a 1/3, 2/3 split. So 2/3 of 1.714. 1.1426, blah, blah, blah. So it's about 1.1. amps. Now, since 3 and 4 are in series, both must have the same current. So I'm going to put 1.1 for both of them because they're in series. Okay, once I find the current that goes through R3, 4, I've basically found the current that goes through 3 and 4. And since 3 and 4 are in series, of course they will have the same current. Okay. The other approach, and if you didn't want to use the current splitter rule, technically you don't have to. You could find the voltages first instead. After you find the total current and notice that the first resistor gets all of it, you can actually find V1. Right? V1 is equal to I1 times R1. Let's go and fill in the chart using Ohm's law. V1 is equal to I1 R1. So everything has to come together now. So we have 5 times 1.7, 5 times 1.714, blah, 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 8.57. So it's about 8.6. 8.6 volts. If I did 5 times 1.7, it's 8.5. Alright, I rounded up slightly because the current was slightly off. I guess I should just, since I'm using Ohm's law, I'll keep it. I guess I'll keep it as is. Okay. We can do R2 times I2, we can do R3 times I3, etc., etc. Or we can do a loop rule, and that is to realize that current can only flow one pathway at a time. Okay, so if I were to take this orange route, the orange route is to go through the battery, of course, through resistor 1 and then through resistor 2, and after going through resistor 2 we're kind of done. It's the end of our journey. And the other option is to do the same, go through resistor 1, but instead of going through 2 we would skip and go through 3 and 4 instead, and then we can come back to the battery. So these are our two pathways that we can take if we were little tiny charges flowing in the circuit. Okay. Therefore, if I lose 8.5 volts in resistor 1, and we're going to lose 8.5 volts no matter what, whichever pathway we take, that means there's how many? 3.5 volts left, right? Because the total is 12, and I'm losing 8.5. It's kind of like paying your fees. When you take R1, you got to pay a fine, and that's 8.5 volts. So you lost 8.5. You have 3.5 left over. That means that resistor 2 should be 3.5. So you could do it that way, in that voltage 2 should equal the total minus V1. But it should also equal I2 R2. And if we see that they're pretty much equal, you might have a little bit of rounding error. It might be off by 100th or something like that, but that's due to rounding error. If you use more sig figs, it works out pretty nicely. So let's see, 6 times 0.57 gives me 3.42, and this one gives me 3.5. So we're close. This gives me 3.42. This gives me 3.5. Right. I'll use 3.5. Yeah. So if you used more sig figs, the numbers would be much closer to each other. And then 3 and 4 will split up proportionally, 2/3 and 1/3 again, in voltages this time instead of current. V3, or just use Ohm's law. I3 R3. 1.1 times 2 is 2.2. Now 2.2 and 1.1 gives me 3.3. So I'm kind of off a little bit. I think I'm going to skip the power. This is just power is equal to IV. Now, if I were to use 3 sig figs, these values would be much closer together. Let's see. If I use 3 sig figs, then I total would be 1.71. So if I had a much better instrument to make the measurements, then of course we would see these patterns work together. Because you might be thinking, wait, that's not the same. Well, this is real life stuff, so it's going to depend on what kind of instrument you use to make measurements of. And if you have a better instrument, then yeah, they will work out. So if with 3 sig figs, my total was 7.17. This would mean that 1.71. This would change our voltage at the start, V1. So V1, let's see, V1 is 1.71 times R1, which is 5. And this would give us V1 as, so with, let's do a different chart here, with 3 sig figs, I1 would equal 1.71 amps. That means V1 would equal 8.55 volts. That means V2, which is a leftover, would equal 12 minus 8.55. What's 12 minus 8.55? 3.45. 3.45. So now we're getting much closer, right? If I found the currents, current divider rule would give me something similar. So 1.71. So let's see. The current divider rule would be 1/3 of 1.71. Oh yeah. Oh, whoops! I did use the raw values for current divider rule. And if I, instead of doing it from subtracting from 12, or I could do I2 R2, and this would be 0.57 times 6, 0.57 times 6, which is 3.42. So as you can see, using Ohm's law or using the subtraction method of adding up voltages, which is called a loop rule, we get a much closer answer. They're almost the same, right? And this would make the current in current in resistor 3,4, which is equal to current in 3, which is equal to current in, because they're in series, would be the total current minus the current in resistor 2, because it does split up into two parts. So if I subtract it from the total, it should give me the leftover. The current in number 2, what was the current in number 2? 0.57. So that means we get total, which is 1.71 minus 0.57, and when we subtract, we actually use the least amount of decimal places, so we have to keep our values to the hundredths place. 1.71 minus 0.57, and that gives me 1.14. Instead of 1.1, I would have 1.14 amps, right? And now you can see how the voltages are even closer together. V2 would be equal to V3 would be equal to I3R3, and this means that it's 1.14 times resistor 3, which is 2 ohms, 2.00, times 2 is 2.28, and V4 would be 1 times 1.14 equals 1.14 volts. Okay, so now they are much closer together. You can see that 2.28 plus 1.14 is equal to 3.42, and that's because voltages in parallel branches, not just parallel resistors, but parallel branches have the same voltages, right? So if I look at the second picture here, whatever voltage is dropped at R2 must be equal to the voltage that is dropped at R34. And since 3 and 4 are in series, the voltage at 3 plus the voltage at 4 must equal the voltage at 2. Okay. So let me say that one more time. So here are, so here are all the things that we can state or conclude about the circuit. Of course, we can say that the total current is I1, right? We use current divider rule. We can say that the voltage at number 2 should be equal to the voltage at 3, 4, because number 2 is parallel to the combination of 3 and 4. Okay? When you have parallel branches, the parallel branches have the same voltage. It's not equal to the battery voltage because these two resistors are not parallel to the battery. That's because resistor 1 is in the way. That resistor 1 in the front kind of changes everything. However, in minor pockets or local clusters, the rules still apply. Since 3 and 4 are in series, resistor 3 and 4 are in series, then the current in resistor 3 should equal the current in resistor 4 because they are in series. So this is because parallel branches this is because they are series resistors. And the only reason we concluded that I total is equal to I1 is because there's no other pathway for the current to go. As soon as it comes out of the battery, it has to go through resistor 1, so that's why it's the total. So in addition to using current splitter rule, in addition to using Ohm's law, You also have to use the rules for series and parallel branches when you're analyzing complex circuits like this. All right. And the last thing to note is that using more sig figs uh, will mean that whichever method you use to solve your circuit, they're more likely to correlate. They're more likely to give you the same values. So if I were to give problems on a test or a quiz, I'll be sure to make it 3 sig figs so that the values are much closer together. All right. Well, I suppose that is all. Remember, Wednesdays we teachers have meetings from now on, so no streams on Wednesdays. You just work on your mastering physics and stuff. Thanks for tuning in. I'll see you next time.